Hello, friend. Welcome. If you're here right now, listening to these words, then you've decided to take a journey with me tonight. A journey into darkness, but not the kind that frightens, the kind that soothes, the kind that holds mysteries so beautiful they might just help you drift away into the most peaceful sleep. Tonight, we're going to explore black holes. Not with fear or urgency, but with wonder. With the kind of gentle curiosity that asks questions without needing immediate answers. So find a comfortable position. Let your shoulders drop. Let your breathing slow. And let's begin this journey together into the places where time bends, where light surrenders, and where the universe keeps its most beautiful secrets. Imagine, if you will, that time itself could stretch. Not metaphorically, but actually physically stretch like warm honey dripping from a spoon on a summer afternoon. Imagine that the seconds you experience could become minutes for someone else, or that hours could expand into days. This isn't fantasy. This is what happens near a black hole. And the closer you get to one of these cosmic giants, the more dramatic this stretching becomes. It's called gravitational time dilation, and it's one of the most peaceful paradoxes in all of physics. You see, Einstein taught us something profound and strange. He showed us that space and time aren't separate things, fixed and rigid like a stage where events play out. Instead, they're woven together into something called space-time, and this fabric can bend and curve and stretch, especially around massive objects. And nothing is more massive, more dense, more concentrated than a black hole. Picture two travelers, twins perhaps, standing at a safe distance from a black hole. One decides to venture closer, to approach the edge of that darkness while the other remains behind. To the twin who stays back, watching through a telescope, something extraordinary happens. Their sibling begins to move in slow motion. Every gesture takes longer. Every step seems to stretch across minutes. The light from their spacesuit begins to shift, becoming redder and redder as time itself dilates around them. But here's the beautiful part. To the twin approaching the black hole, nothing feels different. Their clock ticks normally. Their heart beats at its regular rhythm. They move through time exactly as they always have. It's only in comparison, only in relation to the other, that time reveals its flexibility. This is what's so mesmerizing about black holes. They don't just live in space. They reshape the very fabric of when and where. If you could hover just outside the event horizon, that invisible boundary where a black hole's gravity becomes inescapable, and you stayed there for just 1 hour, decades might pass for the rest of the universe. Your family would age. Civilizations would rise and fall. Stars would be born and die. And yet, for you, only 60 minutes would have passed. You'd return to find a world transformed, a future you never lived through, all because you stood still in a place where time itself moved differently. It's like pressing pause on your own existence while the universe fast-forwards around you. There's something almost tender about this, isn't there? The idea that time is not the tyrant we sometimes think it is, rushing us forward against our will. Instead, it's something soft, something that can bend and stretch and slow, depending on where you are and how fast you're moving. Scientists sometimes describe falling into a black hole as a one-way journey through time as much as space. Once you cross that event horizon, every direction you could possibly move leads you forward in time and inward in space. The future becomes inevitable in a way that's almost poetic. You're no longer moving through time. You're falling through it, the way a leaf falls through autumn air, pulled by something stronger than itself. And as you fall, time outside speeds up relative to you. If you could look back at the universe you left behind, you'd see it aging in fast motion, stars living and dying in what seems like moments, the cosmos spinning through its vast cycles while you drift deeper into darkness. Time, near a black hole, becomes less like a river and more like an ocean, deep and strange and full of currents we're only beginning to understand. There's comfort in this somehow. The reminder that time is not absolute, that the moments we have are not measured the same way everywhere in the universe, that somewhere, somehow, time might stretch long enough for us to see everything we've ever wanted to see, or slow down enough for us to savor what matters most. Black holes teach us that reality is gentler, stranger, and more flexible than we imagine. And perhaps that's worth holding on to as you drift towards sleep. The knowledge that time itself can bend, that nothing is quite as fixed as it seems, that the universe is full of soft edges and gentle transformations. Now, let's consider something that might surprise you. Despite their name, black holes aren't actually holes at all. They're not empty spaces in the fabric of the cosmos, not voids or vacuums or absences. They're quite the opposite, in fact. Black holes are among the most solid, most dense, most present objects in the entire universe. They're the collapsed cores of massive stars, crushed down by gravity into something almost impossibly compact. Imagine taking something as large as our Sun, with all its mass and energy, and compressing it down smaller and smaller and smaller until it occupies a space no bigger than a city. Then keep compressing. Smaller than a mountain, smaller than a building, smaller than a marble. Keep going, past the limits of what seems possible, until all that mass occupies a point infinitesimally small, a place where density becomes infinite. This is what lies at the heart of every black hole. A singularity, they call it. A point where the normal rules break down, where matter is compressed beyond comprehension. It's hard to wrap our minds around, isn't it? How can something be infinitely dense? How can all that mass fit into a space with no dimensions? It defies our everyday experience, challenges our intuition. But that's what the mathematics tells us, and that's what the physics describes. At the very center of a black hole, all the matter that collapsed to create it exists in a state we can barely describe, let alone understand. It's there, definitely there, more there than almost anything else in the universe, but in a form so concentrated, so fundamentally transformed, that it becomes something new, something we're still learning to comprehend. The event horizon that surrounds this singularity, that dark sphere that gives the black hole its name, isn't the object itself. It's just the boundary, the point of no return. Behind that boundary is where the real substance lies, hidden from view, but undeniably present. Think of it this way. A black hole is like the densest knot in the fabric of space-time. While everything else in the universe is spread out, diffuse, separated by vast distances, a black hole is matter's final concession to gravity, its ultimate compression. It's what happens when nothing can resist the pull anymore, when the force of gravity becomes so strong that not even the pressure of atoms pushing against each other can hold matter apart. The star that once shone bright, that once pushed back against its own weight with the fire of nuclear fusion, finally surrenders. It collapses inward in a catastrophic instant, and what remains is this object of incredible density, this point of infinite gravity, this thing we call a black hole, but which is, in truth, the most solid thing imaginable. There's something almost peaceful about this idea too, that even in collapse, even in what seems like destruction, matter doesn't disappear. It doesn't vanish into nothingness. It transforms into something more concentrated, more fundamental, more itself than it ever was before. A black hole represents matter in its most essential form, stripped of all pretense, all excess, all the space between things. It's matter taken to its logical conclusion, compressed to its ultimate truth. And in that truth, there's a kind of perfection, a kind of completion. The name we've given these objects is really a misnomer, a historical accident. When scientists first theorized about them, they imagined them as holes in space, places where things could fall through to somewhere else. But that's not what they are. They're not gaps or absences. They're presences, powerful and undeniable, the most concentrated form of existence in the cosmos. So when you think of black holes tonight, try to remember this. They're not empty. They're not nothing. They're everything, all at once, pressed together so tightly that they become invisible to us, hidden behind their own gravity. And maybe there's something beautiful in that. The idea that the most powerful things are often the things we cannot see directly, but only know by their effects on everything around them, like love or memory, or the force that pulls us towards sleep when we're tired. Present, powerful, but just beyond the reach of direct observation. And speaking of things we cannot see but know are there, did you know that black holes sing? In the deepest darkness of space, in the most silent voids between galaxies, there is music. Not the kind we're used to, not melodies you could hum or rhythms you could tap your foot to, but music nonetheless. Sound waves, vast and low and ancient, rippling through space itself. This discovery is one of the most hauntingly beautiful things science has revealed in recent years, because for so long we thought of space as silent. The vacuum, we were taught, carries no sound. There's no air to vibrate, no medium for sound waves to travel through. And in most of space, that's true. But black holes, particularly supermassive black holes at the centers of galaxies, exist in regions that aren't quite empty. They're surrounded by hot gas, by plasma, by clouds of matter that, while incredibly diffuse by our standards, are dense enough to carry waves of pressure, sound waves, music. In 2003, NASA scientists analyzed data from the Chandra X-ray Observatory pointed at the Perseus galaxy cluster, a collection of thousands of galaxies held together by gravity. At the center of this cluster sits a supermassive black hole, billions of times more massive than our Sun. And this black hole is singing. It's producing pressure waves that ripple through the hot gas surrounding it, sound waves with a wavelength millions of light years long. When the scientists translated these waves into something we could hear, they discovered the note B flat, 57 octaves below middle C. The deepest note ever detected in the universe. A note so low, so profound, that it's been resonating for over 2 billion years. Imagine that for a moment. A song that's older than complex life on Earth. A melody that's been playing since before our solar system formed. A hum that permeates millions of light years of space. This isn't music the way we usually think of it. You couldn't dance to it. You couldn't play it on any instrument humans have ever made. The frequency is far, far below what our ears can detect, waves so slow that they take millions of years to complete a single oscillation. But it is, fundamentally, sound. Vibrations traveling through a medium, pressure waves moving through space. The black hole creates these waves through various mechanisms. Sometimes matter falling into it releases tremendous energy that pushes against the surrounding gas. Sometimes jets of particles shooting out from near the event horizon at nearly the speed of light create shock waves. Sometimes the black hole's gravity itself, warping and distorting space-time, causes ripples in the fabric of reality that manifest as pressure waves in the matter nearby. What makes this so extraordinary is what it reveals about black holes. They're not just passive objects sitting quietly in the darkness. They're active, dynamic, constantly interacting with their environment. They stir the cosmic pot, sending out waves of energy and sound that shape the galaxies around them. These sound waves can prevent gas from cooling and forming new stars, or they can compress gas and trigger star formation. The songs of black holes are not just beautiful in an abstract sense. They're functional, influential, shaping the evolution of the cosmos itself. When you look at images of galaxies, you're seeing structures partially sculpted by the music of their central black holes. The spiral arms, the distribution of stars, the way matter flows and collects, all of it dances, in a sense, to a tune played by darkness. There's something deeply soothing about this idea, that even in the places we think of as most empty, most silent, most void, there is sound, there is vibration, there is something akin to song. The universe is never truly quiet. Even black holes, those ultimate consumers of light and matter, give something back. They hum their ancient notes, patient and endless, and the cosmos resonates in response. As you lie here tonight, breathing slowly, sinking towards sleep, you might find comfort in knowing that even the darkest places in existence are filled with music we're only just learning to hear. Somewhere, right now, a black hole is singing a note that began before human beings existed, and it will continue long after we're gone. It's a lullaby of sorts for a universe that's always been more alive, more musical, more full of gentle sound than we ever imagined. Let that thought soften you. The music of the void, the songs that darkness sings, and let yourself drift on those waves, those impossibly long, impossibly deep oscillations that move through everything, connecting all of space in a harmony we're only beginning to comprehend. Nothing in this universe is truly silent. Everything vibrates, everything sings. Even you, even now, are part of that cosmic chorus. Now, consider light itself. Light that travels faster than anything else we know, that crosses the distance from the sun to Earth in just 8 minutes, that seems unstoppable, eternal, always moving forward at its impossible speed. Light which has never known stillness since the moment of the Big Bang, which has journeyed across billions of light years from the most distant galaxies. Even light, when it encounters a black hole, must surrender. This is perhaps the defining characteristic of these objects, the reason for their name. At the event horizon, that invisible boundary surrounding every black hole, light itself cannot escape. It crosses that threshold and is claimed by the darkness, pulled inward by gravity so strong that even moving at the speed of light isn't fast enough to break free. Think about what that means for a moment. The escape velocity is the speed you'd need to break free from a gravitational pull. On Earth, it's about 11 kilometers per second, which is why rockets need such powerful engines to reach space. On a more massive planet, the escape velocity would be higher. On something incredibly dense, it becomes higher still. At the event horizon of a black hole, the escape velocity reaches the speed of light itself, 300,000 kilometers per second. Nothing in the universe can move faster than that. So anything that crosses that boundary, anything at all, is caught forever. Not because it's stuck or trapped in some mechanical sense, but because there is literally no direction it can move, no path it can take that leads outward. Every possible trajectory points inward, toward the singularity at the center. Light behaves in ways that seem almost alive when it approaches a black hole. Photons, those massless particles of light, travel in straight lines through normal space. But near a black hole, space itself is so curved that straight lines become arcs. Light that passes near a black hole but not too close will have its path bent, gravitationally lensed, like how a glass lens bends light. It curves around the massive object and continues on its way, just in a different direction. This is how we can sometimes see galaxies or stars that are directly behind black holes. Their light bends around the darkness, creating multiple images, Einstein rings, beautiful distortions that reveal the invisible object warping space. But there's a region even closer to the black hole, just outside the event horizon, called the photon sphere. Here, gravity is so strong that light can actually orbit. Photons circle the black hole at exactly the speed of light, trapped in eternal loops, neither falling in nor escaping. If you could somehow position yourself at just the right distance, just the right angle, you could theoretically see the back of your own head. Light leaving the back of your head would curve around the black hole and return to your eyes from the front. It's a realm where geometry becomes strange, where the normal rules of optics and perspective break down into something dreamlike and impossible. And then, the event horizon itself, the point of no return. Here, light crosses from the realm of possibility into inevitability. A photon that crosses this boundary will never escape. It will spiral inward, falling faster and faster, though from the perspective of someone watching from outside, it would seem to slow down, redshift, fade away, but never quite disappear. Time dilation means that as something approaches the event horizon, it appears to freeze from an outside perspective, eternally hovering at that boundary, getting redder and dimmer, but never fully crossing. Yet, from the perspective of the light itself, if such a thing could have a perspective, the crossing happens in an instant. One moment outside, the next moment inside, falling toward the center where all trajectories end. This is why we see blackness. Not because black holes emit darkness, but because they capture light so completely that none returns to our eyes. They're black because they're perfect absorbers, perfect trappers of every photon that comes too close. All the light that has ever fallen into a black hole over millions or billions of years is gone from our universe, at least in the form we can detect. It exists somewhere, somehow, in that compressed space beyond the event horizon, but it will never shine again. There's something almost gentle about this, in a way. Light, which has journeyed so far, which has carried the story of stars and galaxies across the cosmos, finally finds a place where it can rest, where it doesn't have to keep moving, keep bouncing, keep traveling. It crosses that threshold and surrenders to the gravity, joining everything else that has been claimed by the darkness. There are boundaries, even light respects, limits built into the fabric of reality itself. Not everything escapes. Not everything gets to keep moving forever. And maybe that's okay. Maybe there's peace in the idea that even the fastest, brightest things in existence have places where they stop, where they're held, where they become part of something larger than themselves. The light inside a black hole hasn't ceased to exist. It's just transformed, incorporated into something we don't yet fully understand. And as you drift towards sleep tonight, perhaps you can think of rest the same way. Not as an ending, but as a crossing of a gentle boundary into a different state, where the rules change and you're held by something stronger than yourself, something that won't let you fall. But here's something that might surprise you, something that reveals black holes aren't quite as absolute as they seem. Even these perfect trappers of light, these places where nothing escapes, aren't entirely dark. They glow, faintly, almost imperceptibly, but they glow. This is one of the most beautiful discoveries in modern physics, and it comes from the mind of Stephen Hawking, one of the greatest scientists of our time. In 1974, Hawking proposed something radical, something that seemed to contradict everything we knew about black holes. He suggested that black holes aren't completely black, that they emit a form of radiation, now called Hawking radiation, and that over vast stretches of time, this radiation causes black holes to slowly, gradually evaporate. It sounds impossible, doesn't it? How can something escape from a place where escape is impossible? But quantum mechanics, that strange realm of physics that governs the smallest scales of reality, provides an answer that's both counterintuitive and deeply beautiful. At the quantum level, space is never truly empty. This is one of the most profound insights of 20th century physics, even in what we think of as a perfect vacuum. Even in the darkest reaches of intergalactic space, reality seethes with activity. Virtual particles constantly pop into existence in pairs, a particle and its antiparticle, appearing out of nothing, existing for the briefest instant before annihilating each other and disappearing back into the void. These particles borrow energy from the vacuum itself, energy that must be paid back almost immediately. They exist for such fleeting moments that they barely qualify as real, flickering in and out of existence faster than light could cross a single atom. This happens everywhere, all the time, throughout the entire universe. It's a feature of quantum mechanics so fundamental that it's been measured and confirmed in laboratories through something called the Casimir effect. The quantum vacuum, we've learned, is not nothing. It's a roiling sea of potential, a place where particles are always threatening to become real, always on the edge of existence. And nowhere is this more apparent than at the boundary of a black hole, where the fabric of reality is stretched to its absolute limit. Now, imagine these virtual particle pairs appearing right at the event horizon of a black hole. Normally, they'd appear and disappear so quickly that nothing would change. They'd blink into existence, find each other, annihilate, and vanish, all in a time so short that causality itself barely notices. But at the event horizon, something different can happen, something extraordinary. One particle of the pair might fall across the boundary into the black hole, while the other escapes into space. The event horizon separates them before they can reunite and annihilate. When this happens, the particle that escapes becomes real, permanent. It no longer has its partner to annihilate with. It no longer needs to pay back the energy it borrowed from the vacuum. It carries that energy away from the black hole, out into space, becoming part of the ordinary matter and radiation that fills the cosmos. And what about its partner, the particle that fell in? That particle carries negative energy from the black hole's perspective, and when it crosses the event horizon, it effectively subtracts mass from the black hole. This is where the magic happens, where the seemingly impossible becomes possible. Energy cannot be created from nothing. Conservation of energy is one of the most fundamental laws of physics, a rule that governs everything from the smallest quantum events to the largest cosmic structures. So where does the energy for this escaping particle come from? It comes from the black hole itself. The black hole loses a tiny, infinitesimally small amount of mass energy each time a particle escapes in this way. And over time, over unimaginably long stretches of time, this adds up. The black hole slowly radiates away its mass, growing smaller, lighter, gradually evaporating like a puddle in the summer sun, like morning dew on grass, like frost melting from a window. For a black hole the mass of our sun, this process would take 10 to the 67th years. Let's pause for a moment and try to comprehend that number. That's a 1 followed by 67 zeros. It's a number so incomprehensibly large that it makes the current age of the universe, a mere 14 billion years, seem like the blink of an eye. To put it in perspective, if you started with the age of the universe and multiplied it by itself, and then multiplied that result by itself again, and kept doing this over and over, you'd still be nowhere close to 10 to the 67th years. The universe would have to age trillions upon trillions of times longer than it has already existed for a solar mass black hole to evaporate completely. And here's something even more mind-bending. Smaller black holes evaporate faster. Larger ones evaporate slower. This seems backward at first, doesn't it? You might think a smaller black hole would take less time to evaporate, like how a small puddle dries faster than a large one. But the physics of Hawking radiation works differently. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes are hotter and radiate more intensely. A black hole with the mass of a mountain, if one could exist, would glow white-hot and evaporate in fractions of a second, releasing all its energy in a final burst of radiation. But a supermassive black hole, billions of times the mass of the Sun, would be incredibly cold, its Hawking radiation so faint and low energy that it would take times beyond imagination to evaporate. Some of these giants would take 10 to the 100 years or more to fade away completely. But the principle remains, beautiful and inexorable. Nothing lasts forever, not even black holes, those seemingly eternal prisons of light and matter. They're born from collapsing stars. They grow by consuming matter and merging with other black holes. They dominate their regions of space with their immense gravity, and eventually, after time spans that make the word eternity seem brief and inadequate, they fade away into radiation, returning their energy to the universe that created them. It's a slow transformation, a patient unmaking, but it's inevitable. Even the darkest things eventually return to light. The Hawking radiation they emit is incredibly faint, far too faint to detect with our current technology. For all but the smallest black holes, this radiation is cooler than the cosmic microwave background, that faint afterglow of the Big Bang that permeates all of space. the remnant heat from the universe's birth that has cooled to just a few degrees above absolute zero. So black holes right now are actually absorbing more energy from the background radiation than they emit through Hawking radiation. They're growing, not shrinking, at least for now. They're drinking in the ancient photons that have been traveling through space since 380,000 years after the Big Bang, warming themselves, if you can call it that, on the ember glow of creation itself. But wait long enough, far into the deep future, when the universe has expanded and cooled, when the last stars have burned out, and the cosmic microwave background has redshifted into near nothingness, and black holes will become the dominant sources of radiation in the cosmos. They'll glow in the darkness like embers in a dead fire, slowly dimming, slowly fading. The last bright things, however faint that brightness might be, in a cold and empty cosmos. The universe will enter what cosmologists call the black hole era, a time when black holes are the most interesting things still happening, still changing, still releasing energy into the void. And then, eventually, even they will wink out. The smallest ones first, then gradually larger and larger ones, each releasing its final particles into the void, each adding its last contribution to the entropy of the universe. The final black holes will evaporate in bursts of radiation, their last moments spectacular on a quantum scale, if nothing else. And when the last black hole finally evaporates, perhaps trillions upon trillions of years from now, the universe will have entered its final era, what some call the dark era, a time of maximum entropy where nothing interesting can happen anymore, where the universe has reached a kind of equilibrium, cold and dark and unchanging, with nothing left but thin soup of particles spread across an ever-expanding space. There's something profoundly moving about this, isn't there? The idea that even the things we think of as permanent, as unchanging, as eternal, are slowly transforming, slowly giving themselves back to the universe. Nothing lasts forever, not even the eternal dark. Everything is temporary, everything is changing, even on timescales we can barely imagine. Timescales that dwarf our comprehension the way our lifetimes would dwarf the life of a mayfly. The universe has a clock, and it's running, and even black holes aren't exempt from its passage. They're just on a different schedule than we are, marking time in eons while we mark it in heartbeats. Stephen Hawking's discovery of black hole radiation is considered one of the most important insights in theoretical physics, precisely because it reveals this impermanence. It shows us that black holes aren't perfect, aren't absolute, aren't eternal. They're part of the same universal cycle as everything else. They're born, they live, they die, just on timescales that make our entire cosmic epoch seem like a fleeting moment. And there's something almost comforting in that, isn't there? The idea that even the most extreme objects in the universe, even the places where the rules seem to break down completely, are still subject to deeper rules, still part of the great unfolding, still temporary participants in existence. As you lie here, breathing in and out, feeling the weight of your body against the bed, feeling the gentle rise and fall of your chest, you are part of this same process. Temporarily solid, temporarily here, but constantly changing at a level too small to notice. Every 7 years or so, most of the atoms in your body are replaced with new ones. The calcium in your bones cycles through. The cells lining your stomach are replaced every few days. Even the neurons in your brain, once thought to be permanent, are now known to be capable of renewal. You're like a river that keeps its shape while the water flows through, like a flame that maintains its form while consuming different molecules of wax and air, like Hawking radiation in a way, a temporary manifestation of the universe's energy, glowing briefly before returning to the cosmic cycle. And there's peace in that, isn't there? In knowing that nothing is meant to last forever in its current form, that everything, even black holes, is just passing through, just playing its part in the great unfolding of existence. That change isn't something to fear, but something to accept as the fundamental nature of reality. So rest easy. You're exactly where you're meant to be, doing exactly what you're meant to do, which right now is simply to be here, to breathe, and to drift gently towards sleep. You're part of the great cycle, the great transformation, the great return of energy to the universe. And like Hawking radiation escaping from a black hole, you're a temporary manifestation of something larger than yourself, something that will endure even as your current form changes and flows and eventually returns to the stars. Now let's consider something that seems impossible, something that turns our understanding of black holes on its head. Black holes, these great consumers, these cosmic devourers that trap light and matter and let nothing escape, they also create. They give birth. Not in any simple or direct way, but through their influence, through the way they shape and organize and energize the space around them. Black holes help create stars. The very things that eventually become black holes when they die, they also help bring into being. This is one of the most beautiful paradoxes in astronomy, a reminder that in nature, destruction and creation are often two sides of the same process, inseparable and interdependent, woven together in a dance that's been going on since the first galaxies formed. At the center of nearly every large galaxy, including our own, sits a supermassive black hole. These giants are not like the stellar mass black holes formed from collapsed stars. They're different beasts entirely, millions or billions of times more massive than ordinary stars, containing as much mass as entire star clusters, compressed into regions not much larger than our solar system. They exert an enormous gravitational influence on everything around them, holding entire galaxies together, shaping the distribution of stars and gas across hundreds of thousands of light years. They're the anchors of galactic structure, the centers around which everything else orbits. Matter doesn't fall directly into these black holes. Instead, it spirals inward through what's called an accretion disk, a swirling vortex of gas and dust that orbits the black hole in ever-tightening circles before eventually falling in. Think of it like water spiraling down a drain, but on a cosmic scale and moving at substantial fractions of the speed of light. As this matter spirals inward, something remarkable happens. It compresses, heats up, and begins to glow. The closer it gets to the black hole, the faster it moves, and the more it compresses against the material ahead of it. Friction between layers of gas moving at different speeds generates tremendous heat. Temperatures raise to millions of degrees. The matter begins to emit radiation across the entire electromagnetic spectrum, from radio waves to visible light to X-rays. Accretion disks around supermassive black holes can shine brighter than entire galaxies, outshining hundreds of billions of stars combined. Think about that for a moment. An accretion disk that might span only a few light years, a tiny region compared to a galaxy that spans 100,000 light years or more, can emit more light than all the stars in that galaxy combined. This incredible luminosity isn't powered by nuclear fusion like stars. It's powered by something even more efficient, the sheer gravitational potential energy of matter falling into darkness. As matter falls toward a black hole, it converts its gravitational potential energy into kinetic energy, heat and light. Einstein's equation, E equals mc squared, tells us that mass and energy are equivalent, and near a black hole, a significant fraction of an object's mass can be converted into pure energy before it crosses the event horizon. It's one of the most efficient energy generation processes in the universe, far more efficient than nuclear fusion. These are what we call active galactic nuclei, or quasars when they're particularly bright. Quasars are among the most luminous objects in the universe, visible across billions of light-years of space. When we look at distant quasars, we're seeing them as they were in the early universe, when galaxies were young and their central black holes were feeding voraciously on the abundant gas available. Some quasars shine with the brightness of 1 trillion suns, all from a region smaller than our solar system. They're beacons in the cosmic darkness, lighthouses marking the locations of supermassive black holes actively feeding on their surroundings. But here's where it gets interesting, where destruction transforms into creation. The energy released by these accretion disks doesn't just disappear into space. It influences the galaxy around it in profound and complex ways. Powerful jets of particles sometimes shoot out from the poles of the black hole, perpendicular to the accretion disk, traveling at 99% of the speed of light or more. These jets are among the most energetic phenomena in the universe, streams of particles and magnetic fields that can extend for millions of light-years into space, far beyond the galaxy itself. The mechanism that creates these jets isn't fully understood, but it involves the black hole's rotation and the powerful magnetic fields that thread through the accretion disk. Matter that would have fallen into the black hole is instead channeled along magnetic field lines and shot out into space at relativistic speeds. These jets, along with winds of hot gas driven by the radiation pressure from the accretion disk, plow through the galaxy like cosmic snowplows, compressing clouds of gas, stirring up matter, creating shock waves that ripple through the interstellar medium. And here's where creation begins. When gas clouds are compressed, they become denser. When they become dense enough, they can no longer support themselves against their own gravity. They begin to collapse. And when gas clouds collapse, they fragment into smaller clumps, each clump pulling itself together under its own gravity. When these clumps reach sufficient density and temperature at their cores, nuclear fusion ignites. Hydrogen atoms begin to fuse into helium, releasing energy, pushing back against gravity, achieving equilibrium. Stars are born. So the black hole, by feeding, by consuming matter, and releasing tremendous energy in the process, creates the conditions for star formation in its host galaxy. It's a delicate balance, a cosmic dance of forces. Too much energy release, and the gas is blown away entirely, heated to such high temperatures that it can escape the galaxy's gravity altogether, preventing stars from forming. This is called negative feedback, and it's one of the ways black holes regulate star formation in their galaxies. Too little energy release, and the gas remains cold and diffuse, never reaching the densities necessary to collapse and form stars. But in that sweet spot, in that middle range of energy output, black holes sculpt their galaxies into fertile nurseries for new stars. The spiral arms of galaxies, Those beautiful curves we see in telescope images, those graceful arcs studded with bright blue young stars, are partially shaped by the way gas flows under the influence of the central black hole's gravity. Star clusters form along these arms, regions where gas has been compressed by density waves rippling through the galactic disk, waves that are influenced by the massive presence at the center. When you look at a picture of a spiral galaxy like our own Milky Way or Andromeda, you're seeing a structure that's been partly organized by the black hole at its heart. The distribution of stars, the patterns of star formation, the overall architecture of the galaxy, all of it bears the fingerprints of the central black hole's influence. There's also a more direct mechanism, one that's even more dramatic. When two galaxies collide and merge, as happens regularly throughout the universe, their central black holes spiral toward each other like dancers in a slow, inevitable waltz. The collision stirs up enormous amounts of gas, compressing it, heating it, funneling it toward the center where the black holes wait. The merger of two supermassive black holes is one of the most energetic events that can occur in the universe. When they finally come together, they release gravitational waves, ripples in space-time itself that spread out at the speed of light, carrying away a significant fraction of the combined mass as pure energy radiated into the fabric of space. But before that final merger, the collision of the galaxies themselves triggers intense bursts of star formation. The compressed gas clouds collapse in waves, and millions or even billions of new stars can form in a relatively short period, perhaps just a few tens of millions of years. These are called starburst galaxies, and they represent some of the most vigorous star-forming environments in the universe. The black holes, by merging, by releasing that energy, by disturbing the equilibrium of their environment, catalyze creation on a massive scale. They're not passive observers sitting quietly at the centers of their galaxies. They're active participants in the life cycle of galaxies, shaping the rate and location of star formation through their feeding and their energy output. Even the matter that doesn't fall into a black hole plays a role in this cosmic drama. The accretion disk itself can be a site of star formation under certain conditions. If the disk is massive enough and cool enough in its outer regions, parts of it can fragment and collapse into stars that orbit the black hole itself. These stars exist in one of the most extreme environments imaginable, orbiting at tremendous speeds just outside the event horizon, completing their circuits in years or even months, bathed in intense radiation from the accretion disk, but alive nonetheless, burning bright in the shadow of darkness. They're like children raised in a forge, toughened by the extreme conditions, shaped by forces that would destroy most stars. Scientists have observed these stars orbiting Sagittarius A star at the center of our own galaxy. They've tracked individual stars on elliptical orbits that bring them within light hours of the event horizon, closer to a black hole than any other observed stars in the universe. One star, called S2, completes its orbit in just 16 years, reaching speeds of several percent of the speed of light at its closest approach. These stars have likely formed from the material in the accretion disk itself, born in the very environment created by the black hole's feeding. It's a reminder that life and death, creation and destruction, light and darkness, they're not opposites in the way we sometimes think. They're partners, dancers, different aspects of a single process that weaves through the entire cosmos. And there's something even more profound to consider. Without supermassive black holes, galaxies themselves might not be stable. Computer simulations of galaxy formation show that galaxies without central black holes tend to form stars too efficiently, consuming all their gas in a short burst and then going dormant. The feedback from black holes, the energy they pump into their surroundings, is crucial for regulating star formation, for spreading it out over billions of years instead of letting it happen all at once. Black holes act as thermostats for their galaxies, sensing when too much gas is accumulating at the center and releasing energy to heat and disperse it, preventing runaway star formation and maintaining a steady, sustainable rate of stellar birth. So when you think of black holes tonight, try to hold both truths at once in your mind. They consume, yes. They trap light and matter in their inescapable gravity. But they also organize, energize, and create. Without them, galaxies might not have the structure they do, the beautiful spiral arms, the ordered distribution of stars and gas. Stars might not form in the patterns and quantities they do, leading to a very different universe, perhaps one less hospitable to the emergence of complexity and life. In a very real sense, black holes help make the universe a more interesting, more dynamic, more life-filled place. They're gardeners of sorts, pruning and shaping and fertilizing the cosmic landscape, cultivating the conditions for stars and planets, and perhaps eventually for life itself. What devours light also creates it, just in a roundabout way, through forces and mechanisms that remind us how interconnected everything is in this universe. Nothing exists in isolation. Everything influences everything else. The black hole at the center of our galaxy influences the formation of stars, which create the heavy elements necessary for planets, which provide the environments where life can emerge. The iron in your blood was forged in a star, but that star might not have formed without the influence of a black hole organizing the gas cloud from which it was born. And sometimes, the things that seem most destructive, most final, most absolute, are actually essential for creation to occur. The universe needs its destroyers as much as its creators, because often they're the same thing, viewed from different perspectives. Before we move forward, let's pause for a moment and consider something deeper, something that touches on the very nature of reality itself. Black holes don't just challenge our understanding of gravity and space-time. They challenge our understanding of information, of quantum mechanics, of what it means for something to exist at all. There's a question that has puzzled the greatest minds in physics for decades, a puzzle so profound that it's called a paradox. It's the black hole information paradox, and it asks something that sounds simple but cuts to the heart of reality. What happens to information when it falls into a black hole? Does it disappear forever, or is it somehow preserved? In quantum mechanics, information is sacred. It cannot be destroyed. This is one of the most fundamental principles of the quantum world, as basic and inviolable as the conservation of energy. If you know the complete quantum state of a system, all the information about the positions and momenta and spins of every particle, you can in principle calculate what that system was like at any earlier time, or what it will be like at any future time. Information flows forward through time, but it's never lost, never erased, never destroyed. It might become scrambled, mixed up, spread out across many particles, but it's still there, still recoverable in principle. This is called unitarity, and it's a cornerstone of quantum mechanics, tested and confirmed in countless experiments. But black holes seem to break this rule, and that's deeply troubling. When something falls into a black hole and crosses the event horizon, that object carries information with it. Information about its quantum state, its internal structure, the arrangement of all its particles. And once it crosses that boundary, that information seems to be lost forever. The event horizon is a one-way membrane. Nothing can come back out to tell us what happened inside. The information is hidden, trapped, seemingly erased from the universe we can observe and interact with. And when the black hole eventually evaporates through Hawking radiation, billions or trillions of years later, the radiation that emerges appears to be completely thermal, completely random. It's like the light from a hot stove, carrying no specific information about what's generating it, no trace of what fell into the black hole all those eons ago. This creates a profound conflict between two of our most successful theories. General relativity says the information fell into the black hole and is lost behind the horizon. Quantum mechanics says information cannot be destroyed and must somehow be preserved. Both theories have been tested extensively and work beautifully in their respective domains, but they give contradictory answers about black holes. Something has to give. Either quantum mechanics needs to be modified to allow information destruction, which would overturn a century of quantum theory and invalidate countless experiments, or general relativity needs to be modified, or there's some subtle way the information is actually preserved that we haven't understood yet. Stephen Hawking initially argued that information was indeed destroyed in black holes, that this was a real exception to quantum mechanics. In 1976, he published calculations suggesting that black hole evaporation erases information permanently. This would mean quantum mechanics, as we know it, is incomplete or wrong, at least when gravity becomes very strong. It would require a fundamental reformulation of quantum theory, allowing for a kind of information loss that doesn't occur anywhere else in physics. This was revolutionary and troubling. Many physicists pushed back, arguing that information must somehow be preserved, that we were missing something important about how black holes work. The debate raged for decades, becoming one of the central questions in theoretical physics. How could the information be preserved? Some suggested it might remain encoded in subtle correlations in the Hawking radiation, correlations so delicate and spread out that they seem random locally, but actually carry information when you look at the radiation as a whole. Others proposed that information might never truly cross the event horizon, but instead gets smeared out on the horizon's surface, stored there in some quantum state we don't yet understand. This led to fascinating ideas, like the holographic principle. The holographic principle is one of the most mind-bending concepts to emerge from black hole physics. It suggests that all the information about what's inside a three-dimensional volume of space can be encoded on its two-dimensional boundary, much like a hologram encodes three-dimensional images on a two-dimensional surface. Applied to black holes, this means all the information about what fell into the black hole might be stored on the event horizon itself, on that two-dimensional surface, rather than in the three-dimensional interior. The event horizon becomes like a cosmic hard drive, encoding information in quantum bits spread across its surface. If this is true, and many physicists now believe it is, then the information isn't lost. It's stored at the boundary, and when the black hole evaporates, That information is released back into the universe through subtle correlations in the Hawking radiation. The information is preserved, unitarity holds, quantum mechanics survives intact. But this comes at a cost. It suggests that three-dimensional space might itself be a kind of hologram, that the reality we experience might be a projection from information encoded on distant boundaries. Our universe might have fewer dimensions than it appears to have, with the three dimensions of space emerging from a more fundamental two-dimensional description. This is radical. It challenges our most basic intuitions about space and reality. But it's taken seriously because it resolves the information paradox while preserving both quantum mechanics and a modified understanding of how gravity works at quantum scales. It suggests that space itself is not fundamental but emergent, that it arises from deeper quantum information processing happening at boundaries. In this view, the universe is less like a container and more like a computer, processing quantum information according to rules we're still learning. In 2004, Stephen Hawking conceded the debate, announcing that he now believed information was preserved in black holes after all. He suggested that quantum fluctuations near the event horizon might allow information to leak back out in subtle ways. The exact mechanism is still debated, and we don't have a complete theory yet. We're still working on quantum gravity, the theory that would unite quantum mechanics and general relativity and tell us exactly what happens at event horizons and singularities. String theory, loop quantum gravity, and other approaches are being pursued, each offering different perspectives on how quantum effects modify our understanding of black holes. What's beautiful about all this is that black holes, these objects that seem so remote and extreme, are teaching us fundamental truths about reality itself. They're showing us that space and time might not be what they seem, that information is more fundamental than matter, that the universe might be holographic, that our theories need to be unified in ways we haven't achieved yet. Black holes are laboratories for testing the most extreme physics, places where nature pushes its own rules to the breaking point and forces us to think more deeply about what's really going on. And there's something almost comforting in this uncertainty, in knowing that we don't have all the answers yet, that there are still deep mysteries waiting to be solved. It means the universe is richer and stranger than we currently understand. It means there are still discoveries to be made, insights to be gained, moments of revelation ahead when someone figures out how it all fits together. Black holes guard these secrets jealously, hiding them behind event horizons we can never cross and return from. But they give us clues through their behavior, their radiation, their effects on everything around them. They're teaching us, patiently, gradually, revealing the deep structure of reality, one insight at a time. As you settle deeper into rest now, into that state between waking and sleeping, where thoughts become fluid and boundaries blur, think about information. Your consciousness right now is a pattern of information processing in your brain, neurons firing in particular sequences, creating the sense of you, of awareness, of being here in this moment. When you sleep, that pattern changes but isn't destroyed. It's transformed, reorganized, different, but not gone. And even when you eventually die, the atoms that carried that information will persist, will go on to form new patterns, new structures, perhaps eventually contributing to new consciousness in forms we can't imagine. Information transforms, but endures. Nothing is truly lost. Everything is recycled, reimagined, preserved in new configurations. As you drift now toward the edge of sleep, imagine that process. The way endings become beginnings. The way what falls into darkness emerges again as light, transformed but not lost. Everything in the universe is recycled, reimagined, reborn. The atoms in your body have been through countless cycles already. They were forged in the cores of ancient stars, scattered through space in supernova explosions, gathered into new clouds of gas and dust, formed into new stars and planets, and eventually incorporated into you. And when you're gone, those atoms will continue their journey. They'll return to the cosmos, perhaps one day to be part of a star again, or a planet, or another living being. The circle continues endlessly, creation flowing from destruction, destruction enabling creation, and black holes standing at the center of it all, conducting the orchestra with their immense gravity, including you, eventually, your atoms returning to the cosmos, perhaps one day to be part of a star, or a planet, or another living being experiencing wonder, just as you are now. The circle continues. The dance goes on, and will go on for billions of years to come. And black holes, those mysterious hearts of galaxies, keep the rhythm, keep the pace, conducting the grand orchestra of creation with their immense gravity, their powerful energy, their organizing influence on the structure of everything around them. There's something else you should know, something that brings all this a little closer to home, something that connects you personally to everything we've been discussing. Right now, at this very moment, as you lie here listening to these words, you are orbiting a black hole. It's not close, not dangerously close, but it's there, a constant and patient presence at the center of our galaxy, holding everything together with its enormous mass. We call it Sagittarius A star, or SGR A star for short, pronounced Sagittarius A star by astronomers, and it sits approximately 26,000 light-years away from us, in the direction of the constellation Sagittarius, which rises in the summer sky if you're watching from the northern hemisphere. This black hole is roughly 4 million times more massive than our Sun, containing as much mass as 4 million stars like ours, compressed into a region smaller than the orbit of Mercury. And it's been there, silent and patient and powerful, for most of the history of our galaxy, perhaps 10 billion years or more. We've been dancing around it for billions of years, and never knew it, never suspected it, until very recently in human history. Think about that for a moment. Our Sun, that bright yellow star that gives us warmth and light, that makes life possible on Earth, that we think of as the center of our solar system, is itself orbiting something else. Along with hundreds of billions of other stars, our Sun orbits the galactic center in a vast, slow waltz that's been going on since long before Earth formed. We're moving through space at about 220 kilometers per second relative to the galactic center, which sounds incredibly fast, and it is by human standards. But on galactic scales, it's actually quite leisurely. It takes our Sun roughly 230 million years to complete one full orbit around the center of the Milky Way. Let that sink in for a moment. 230 million years for a single orbit. The last time we were in this exact spot in our orbital path, roughly where we are now relative to the galactic center, dinosaurs were just beginning to emerge on Earth. The Triassic period was beginning. The first dinosaurs were small, lizard-like creatures, nothing like the giants they would eventually become. Pangaea, the supercontinent, was still intact. The next time we return to this exact spot, 230 million years from now, who knows what will have become of humanity, of Earth, of the life we know? Will humans still exist? Will we have spread to other star systems? Will Earth still be habitable? Will the sun still burn as it does now? These are questions we can't answer, timescales we can barely comprehend. But Sagittarius A star will likely still be there, still holding court at the center, still shaping the galaxy with its gravity, patient and eternal on human timescales, even as it slowly evolves on cosmic ones. For most of human history, for all of our existence until the last few decades, we didn't know this black hole existed. We couldn't see it directly because it's hidden behind vast clouds of dust and gas that block visible light. When you look toward the constellation Sagittarius, toward the densest part of the Milky Way band in the sky, you're looking toward the galactic center, but the dust between us and it blocks our view almost completely. In visible light, it's hidden, obscured by the accumulated dust of billions of years of star formation and stellar deaths. But dust can't hide everything. In recent decades, using radio telescopes and infrared observations that can penetrate the dust, seeing wavelengths of light that pass through the obscuring clouds, we've mapped the region around the galactic center in exquisite detail. And what we found was extraordinary. We've watched stars orbiting very close to Sagittarius A star, some of them completing their orbits in just a few years, moving at incredible speeds that boggle the mind, sometimes reaching a few % of the speed of light at their closest approach. These aren't small stars either, but massive, bright stars many times the mass of our Sun. One of them, called S2, has been tracked for over 2 decades now, and astronomers have watched it complete more than one full orbit around the invisible object at the center. At its closest approach, S2 comes within about 17 light hours of Sagittarius A star and is moving at nearly 5% of the speed of light, fast enough to circle Earth's equator over 1,000 times in a single second. By tracking these stars' movements with incredible precision, by measuring how their orbits wobble and shift, by watching how they accelerate and decelerate as they swing around the center, we've been able to calculate the mass of the invisible object they're orbiting. And the answer came back clear, unambiguous, undeniable. Something with a mass of 4 million suns, compressed into a region smaller than Mercury's orbit around our Sun, sits at the center of our galaxy. A black hole, without question. There's no other explanation that fits the observations. No cluster of stars could be that compact without collapsing. No cloud of dark matter could affect the star's orbits in precisely that way. It had to be a black hole, and not just any black hole, but a supermassive one, one of the giants that anchor galaxies. And then, in 2022, we did something that seemed impossible just a few decades ago. We photographed it. Well, not the black hole itself, because by definition it emits no light, but the next best thing, the shadow it creates. Using a network of radio telescopes spread across the entire Earth, from Hawaii to Chile to the South Pole to Spain, working together as a single instrument called the Event Horizon Telescope, scientists captured an image of the shadow of Sagittarius A star. It was one of the most technically challenging observations ever attempted in astronomy, requiring precise coordination between telescopes thousands of miles apart, accounting for Earth's rotation, processing petabytes of data, and using sophisticated algorithms to reconstruct an image from the signals. The result was breathtaking in its simplicity and its significance. The image shows a dark circle, the event horizon's shadow, surrounded by a bright, glowing ring of emission from the accretion disk. It's blurry, orangish in the false color image, almost fuzzy around the edges, because Sagittarius A star is actively feeding, and the hot gas around it moves and changes on timescales of minutes. The material orbiting it completes a circuit in just minutes to hours, so the image is actually a kind of average of all that chaotic, swirling motion. But it's unmistakably there, the heart of our galaxy, revealed at last. A darkness we can point to and say, there, right there, that's where we orbit. That's what holds us in this great spiral. That's the anchor of our cosmic home. Sagittarius A star is relatively quiet as supermassive black holes go, at least right now. It's not actively feeding on huge amounts of matter at the moment, not like the quasars we see in distant galaxies. If it were, the center of our galaxy would be a much brighter, much more violent place, potentially hostile to life on planets like Earth. But it's not gorging itself. It's sipping occasionally, taking in wisps of gas, the occasional star that wanders too close, releasing flares of X-rays and infrared light when it feeds. But mostly, it's dormant. It's like a banked fire, glowing embers with occasional sparks when new fuel falls in. Mostly quiet, but always there, always present, always exerting its gravitational pull on everything around it. In the distant past, it may have been much more active, much more violent. There's evidence that just a few million years ago, a time that's recent, by cosmic standards, Sagittarius A star consumed a large amount of matter and released tremendous energy, creating what astronomers call the Fermi bubbles, huge lobes of hot gas extending above and below the galactic plane, visible in gamma-ray light. These bubbles are remnants of a time when our galaxy's heart was more active, when it fed more voraciously and shone more brightly. And in the distant future, it might flare up dramatically again. Perhaps when our galaxy collides with Andromeda in about 4 billion years, and fresh gas is funneled toward the center by the gravitational chaos of the merger. But for now, for this cosmic moment that includes all of human history, and will include likely millions of years more, it waits quietly, and we orbit it peacefully at a safe and comfortable distance. There's something deeply moving about knowing this, about understanding our place in the galactic structure. We're not just floating randomly through space, drifting aimlessly through the void. We're part of a structure, a system, organized by the gravity of a black hole. We're bound to it, connected to it, our path through the cosmos shaped by its presence, even though we can't see it directly, even though it's hidden behind veils of dust, even though it makes no sound we can hear. It's been guiding our sun's journey for longer than complex life has existed on Earth. Every species that ever lived, every person who ever looked up at the night sky and wondered about their place in the universe, every human achievement, every moment of joy or sorrow, every thought anyone has ever had, all of it happened while orbiting that black hole. We've been held by it all along, moved by it, kept in motion by its immense mass. We've been part of its system, its family of stars, and we never even knew. Think about what this means. Every night when you look up at the Milky Way, that band of light stretching across the sky, you're seeing the combined glow of billions of stars, all of them, every single one, orbiting the same center we are. We're all in this together, all part of the same gravitational dance. And at the center of that dance, invisible but undeniable, sits Sagittarius A star, the dark heart of our galaxy, the anchor that holds everything in place. Without it, our galaxy would fly apart, the stars scattering into intergalactic space. It's the gravitational glue that keeps us all together, that maintains the spiral structure that ensures we remain part of this collection of stars rather than wandering alone through the cosmic void. As you lie here tonight, breathing slowly, feeling the weight of your body against the bed, feeling yourself settling into comfort and peace, you might take comfort in this knowledge as well. We're not adrift. We're not lost. We're not wandering aimlessly through an uncaring universe. We're part of something larger, something ancient, something that's been turning for billions of years with a stately grace that makes our hurried lives seem like the beat of a hummingbird's wings. The galaxy is our home, our cosmic neighborhood, and at its heart is a mystery, a darkness that holds everything together. We orbit it the way children orbit their parents, held in place by forces we don't fully control or understand, but which keep us safe, keep us moving in stable paths, keep us part of the great dance rather than lost in the darkness. So rest easy. You're exactly where you belong. You're in orbit, as you've always been, around a center you can't see, but which has always been there, always will be there on human timescales. You're part of a system that's older than you can imagine and will continue long after you're gone. Your sun is orbiting a black hole and has been since before Earth formed, since before the first living cells emerged in ancient oceans, since before consciousness arose to contemplate its own existence. And it will keep orbiting, carrying Earth along with it, carrying future generations, carrying whatever comes after us, for hundreds of millions of years to come. We're all travelers together, moving through space at hundreds of kilometers per second, swept along by the gravity of a black hole that holds the galaxy together. And there's something profoundly comforting in that, in knowing we're part of something so much larger than ourselves, so much more enduring than our brief lives, something that connects us to every other star, every other world, every other potential civilization in our galaxy. We're all orbiting the same center. We're all part of the same cosmic family. And at the heart of that family, silent and patient, sits Sagittarius A star, holding us all in its gravitational embrace. Now, before we drift into our final thoughts, before we let sleep take us completely, there's one more thing worth knowing, one more image worth holding as you sink toward dreams. If you could somehow fall into a black hole, if you approached that boundary and crossed it, and continued inward toward the singularity at the heart, something strange and almost beautiful would happen to your body. You would stretch, gently at first, then more dramatically, pulled longer and thinner like taffy being stretched on a summer day, like dough being rolled out, like a thought becoming a dream, like a memory fading and elongating until it's barely recognizable. Scientists call this spaghettification, a slightly silly term, almost whimsical, for something that's both terrible in its finality and oddly graceful in its geometry. The process by which tidal forces stretch you into a strand, a thread, an infinitely thin line of what you once were. Here's why it happens, and the physics behind it is actually quite simple, even beautiful in its inevitability. Gravity doesn't pull equally on all parts of an object. The force of gravity decreases with distance, following an inverse square law that goes back to Newton. The closer you are to the source of gravity, the stronger the pull. On Earth, where the gravitational field is relatively uniform and we're all far from the center, the difference in gravitational pull between your head and your feet is negligible, too small to notice, just a tiny fraction of your weight. Your body experiences gravity as essentially uniform, pulling downward with the same force everywhere. But near a black hole, especially a smaller one, where the event horizon is close to the singularity, that difference becomes extreme, dramatic, eventually overwhelming. If you fell in feet first toward a stellar mass black hole, one formed from a collapsed star just a few times the mass of our Sun, your feet would experience much stronger gravity than your head. The difference might seem small at first, just a gentle stretching sensation, like someone was pulling on your legs. But as you got closer to the event horizon, that difference would grow. Your feet, being closer to the black hole, would be accelerated more strongly than your head. The gap would widen. You'd begin to stretch in earnest, your body elongating against your will, your bones and muscles and tendons pulled taut, then beyond taut, then beyond any limit they could withstand. At the same time, you'd be compressed from the sides. Gravity doesn't just pull you downward toward the center. It pulls you inward from all directions. The fabric of space itself funnels toward the singularity, and you would be squeezed as you were stretched, compressed horizontally, even as you were extended vertically. The result is transformation into a long, thin strand of atoms. Your body losing its familiar shape, becoming linear, one-dimensional almost. A string of particles arranged in a line from what was once your feet to what was once your head. With a stellar mass black hole, one formed from a collapsed star and only a few times the Sun's mass, spaghettification would begin well before you reached the event horizon. The tidal forces would tear you apart painfully and dramatically, ripping you into constituent atoms, then perhaps even ripping apart the atoms themselves, separating electrons from nuclei long before you crossed the point of no return. You'd be destroyed by forces so extreme that death would be instantaneous. Your consciousness ended before any pain signal could travel along nerves that no longer existed. It would be a violent end, but so quick as to be almost merciful in its totality. But here's where it gets interesting, where the size of the black hole matters enormously. With a supermassive black hole like Sagittarius A star, something fundamentally different happens. Because it's so much more massive, millions or billions of times the mass of our Sun, its event horizon is much farther from the singularity at the center. The curvature of space near the event horizon is actually relatively gentle, at least compared to a smaller black hole. The tidal forces at the horizon itself are weak enough that you could cross it without feeling anything unusual at first. You'd be doomed, of course, with absolutely no possibility of return, cut off from the rest of the universe forever. But you'd still be intact, still yourself, still conscious and aware, at least for a while longer. This is one of the strangest things about black holes. For a supermassive one, crossing the event horizon might not even be noticeable. There's no physical barrier there, no wall or membrane, no sudden change in anything you could measure locally. You just glide across, the way a boat passes an invisible line of longitude, unaware that you just crossed the point of no return. Light from behind, you could still reach your eyes. You could still look back and see the universe you left, though it would appear strangely distorted, Blue shifted, perhaps, time appearing to speed up for the outside world from your perspective. But ahead of you, toward the singularity, there would be only darkness, because no light from inside can reach your eyes from that direction. Only as you fell deeper, approaching the singularity at the center of the supermassive black hole, would the tidal forces grow stronger. And by then, time would be behaving so strangely relative to the outside universe that the experience would be difficult to describe. From your perspective, falling inward, you'd accelerate faster and faster, pulled toward the center by irresistible gravity. The tidal forces would intensify gradually, then more rapidly. You'd begin to feel the stretching, the pressure, your body elongating despite any resistance. The stretching would intensify until, at some point, that depends on the specific black hole's mass. And your distance from the singularity, you'd be torn apart into your component particles, unmade, transformed from a coherent organism into a stream of atoms all falling in the same direction toward the same inevitable end. But from the perspective of someone watching from outside, someone hovering safely beyond the event horizon with a powerful telescope trained on you, something very different would appear to happen. They'd never see you cross the event horizon. Time dilation would cause your image to slow down asymptotically as you approached the boundary. Your movements would become slower and slower. Your clock would appear to tick more and more gradually. The light from your body would redshift, becoming redder and redder, dimmer and dimmer, as the photons struggled to escape the deepening gravitational well. Eventually, you'd appear to freeze at the event horizon, your image growing so dim and so red that it would fade from view entirely, but never quite disappearing, never quite crossing. You'd appear to hang there forever, eternally hovering at the boundary, a ghost image slowly fading into invisibility. Both perspectives are valid, both are real in their own reference frames, and this is part of what makes black holes so philosophically fascinating. To you falling in, the crossing would happen in finite time, perhaps just seconds or minutes. To someone outside, it would take forever, literally, for you to cross. Which version is true? Both are. Reality itself fractures at the event horizon into different perspectives that can never be reconciled, because no information can pass from inside to outside to allow comparison. It's a fundamental limit written into the structure of space-time. There's a strange beauty in all this, if you can set aside the horror of being pulled apart, the violence of the transformation. The idea that in the moments before complete dissolution, you'd be stretched so thin that you'd become almost one-dimensional, a line in space, matter extended to its geometric limit. You'd be unmade, yes, destructively and irreversibly, but unmade into something geometrically simple, elegant even, pure in its form. A string of atoms aligned perfectly, pulled taut by gravity, strung between the event horizon and the singularity like a wire vibrating with your last moments of existence. And then, at the singularity itself, another transformation we cannot comprehend or describe, into a state where space and time lose their meaning, and all the rules we know break down into quantum foam and mathematical singularities. Some physicists wonder if the singularity is even real, or just a sign that our theories break down, that our equations fail when pushed to these extremes. Perhaps there's something else there, some quantum structure we don't yet understand, some mechanism that prevents true infinite density and resolves the singularity into something finite but strange. Perhaps falling into a black hole leads somewhere some other region of space-time, some other universe even, through a wormhole or bridge we cannot yet describe mathematically. We don't know. We may never know, because nothing that crosses the event horizon can send information back out to tell us what it found. The singularity keeps its secrets absolutely. But the process of falling, that gentle then sudden stretching, that transformation from person to strand to stream of particles, that's something we can calculate, something we can describe with confidence using Einstein's equations. It's real, or as real as anything can be in these extreme circumstances. And if we imagine this process not with fear but with curiosity, with a kind of detached wonder, there's something almost meditative about it. The letting go of form, the stretching beyond boundaries, the transformation into something new and strange. Your body would become a different geometry, a different topology, extended through space in a way it never was before. In your own way, falling asleep is a little like this, isn't it? Not physically, of course, but metaphorically, symbolically. You stretch out, you relax, you let the boundaries of your consciousness soften and blur. You become less defined, more diffuse, your thoughts elongating and breaking apart until they're no longer quite thoughts but something else, something dreamlike and fluid, something that flows rather than maintains structure. You cross your own event horizon into sleep, and there's no going back until morning pulls you out again. But in that crossing, there's a kind of grace, a surrender to forces larger than yourself, a willingness to be transformed, however temporarily, into a different state of being. Even in being unmade, there is beauty. Even in dissolution, there is a kind of peace, a release from the rigid structures that define us. The black hole does to matter what sleep does to consciousness, transforms it, takes it apart gently at first, and then more thoroughly, and incorporates it into something larger and less individual than what it was before. And maybe that's okay. Maybe that's even comforting in its way. To know that there are forces in the universe strong enough to change everything we are, to transform us so completely that we become unrecognizable, but which do so according to laws, according to patterns, according to the deep mathematical structure of reality. The universe doesn't act capriciously. It follows rules, even in its most extreme environments. And there's something soothing in that, in the predictability, in the inevitability, in the way that even destruction follows beautiful equations. So as you stretch out now, as you lengthen your body against the bed, as you feel your limbs extending and your muscles relaxing, think of spaghettification not as something violent, but as a kind of ultimate relaxation, a complete surrender to gravity, a transformation into pure linearity. You don't have to resist anymore. You can just fall, just stretch, just let go completely. The universe will do the rest, pulling you gently into new configurations, new states of being, whether that's sleep in this moment or whatever comes after, when your atoms eventually return to the cosmos. For now, just let yourself be pulled toward rest, toward dreams, toward that soft darkness where the boundaries dissolve, and you become something less defined and more fluid than your waking self. So we come now to the end of our journey, to the last thoughts before sleep takes you completely, before you cross that gentle boundary into dreams. We've traveled together through the strange and beautiful territories of black holes, these objects that exist at the very edge of what's possible in our universe, these cosmic extremes that challenge everything we think we know about reality. We've explored how they bend time itself, making it stretch like honey, like fabric, like the moments between heartbeats. We've learned that despite their name, they're not wholes at all, but the most concentrated, most present objects in existence, matter compressed to its ultimate limit. We've heard their songs, those impossibly deep notes that resonate through space for billions of years. We've watched light surrender to them, giving up its eternal motion and falling into darkness. We've discovered that even they glow faintly, returning their mass to the universe over timescales that dwarf imagination. We've seen how they create as much as they destroy, birthing stars even as they consume matter, shaping galaxies with their gravity and their energy. We've learned that we orbit one, that right now, this moment, we're part of a system held together by Sagittarius A star, that invisible anchor at the center of the Milky Way. And we've imagined what it would be like to fall into one, to be stretched and transformed, unmade and incorporated into something beyond our comprehension. And what have we learned from all this? What wisdom can we take from these cosmic extremes into sleep with us? Perhaps that the universe is stranger than we imagine, more flexible in its rules, more poetic in its structure than the rigid certainties we sometimes crave. Black holes show us that time is not absolute, that it can bend and stretch and slow depending on where you are and how fast you're moving. This is not metaphor. This is literal truth, confirmed by every experiment we've done, every observation we've made. Time itself is negotiable, changeable, as fluid as water flowing around a stone. And if time can bend, what else in our lives that seems fixed might actually be flexible? What other rules that seem absolute might actually have soft edges, gentle exceptions, places where they transform into something else? Black holes teach us about boundaries and what lies beyond them. The event horizon is a boundary like no other, a point of no return written into the fabric of space-time itself. Once you cross it, every direction leads inward, every path leads forward in time. There's no going back, no escape, no second chances. And yet, it's not a wall. It's not a barrier you can touch or see. It's just a place where the geometry of space changes, where the rules shift, where what was possible becomes impossible, and what was reversible becomes final. Our lives have boundaries too, don't they? Moments we can't return to, decisions that once made cannot be unmade. Thresholds we cross without realizing their significance until we're already on the other side. Black holes remind us that boundaries are real, that some changes are irreversible, but also that boundaries aren't always visible, aren't always marked, aren't always what we expect them to be. They teach us that nothing lasts forever, not even the darkest places, not even the most extreme objects, not even things that seem eternal and unchanging. Through Hawking radiation, black holes slowly evaporate, returning their mass to the universe over incomprehensible spans of time. This is one of the most profound truths physics has revealed. Permanence is an illusion. Everything changes, everything transforms, everything eventually returns to the cosmic cycle. Stars are born, burn bright, and die. Galaxies form, evolve, and eventually exhaust their gas. Even black holes, those seemingly eternal prisons of light, fade away given enough time. And us, we're part of that same cycle, that same great transformation. We're temporary arrangements of atoms, patterns that persist for a while before dissolving back into the universe that made us. And there's peace in that, isn't there? In knowing that impermanence is universal, that nothing is supposed to last forever, that change is not failure, but the fundamental nature of existence. They teach us that destruction and creation are not opposites, but partners, two aspects of a single process. Black holes consume matter and energy, trapping light that will never escape. But they also organize galaxies, trigger star formation, shape the evolution of cosmic structure. Without them, the universe would be a different place, perhaps a less interesting one, perhaps one less conducive to complexity and life. This is true everywhere in nature, not just in the cosmos. Forest fires destroy but also renew. Autumn strips the leaves but enriches the soil. Death makes room for new life. The universe doesn't waste anything. Everything is recycled, repurposed, reimagined. What seems like an ending is also a beginning. What appears to be destruction is simultaneously creation, just operating on different timescales, different perspectives. Black holes teach us humility, reminding us how small we are compared to these cosmic giants, how brief our lives compared to the billions of years these objects exist, and the trillions more they'll endure. A black hole the mass of our sun would take longer than the current age of the universe, repeated trillions upon trillions of times to evaporate. The black hole at the center of our galaxy has been there for most of galactic history, 10 billion years or more, while human civilization has existed for mere thousands of years, the blink of an eye on that scale. We're brief, ephemeral, tiny flickers of consciousness in a vast and ancient cosmos. And yet, we're also the part of the universe that can understand black holes, that can write equations describing them, that can build telescopes to observe them, that can lie here contemplating their nature. We're small, but we're also significant in our own way, the universe's way of knowing itself, of reflecting on its own structure, of finding beauty in its own mathematics. But they also teach us connection, showing us that we orbit them, that we're bound to them, that we're part of the same structures they help create and maintain. We're not separate from black holes. We're part of the same universe, the same web of gravity and light and matter. The black hole at the center of our galaxy holds us in orbit, shapes the distribution of stars, influences the rate of star formation, and therefore influences the existence of our sun, our Earth, ourselves. We're connected to it even though we can't see it, even though it's 26,000 light years away. And we're connected to all the other stars orbiting it too, billions of them, all part of the same galactic family, all held together by the same invisible anchor. This is true of everything in the universe. Nothing exists in isolation. Everything influences everything else. We're all connected, all part of the same cosmic web, all dancing to the same gravitational music. As you drift now, fully towards sleep, as your breathing slows and deepens, as your thoughts become soft and scattered, let yourself feel held by this knowledge. You exist in a universe that contains black holes, and that's a beautiful thing, a wondrous thing. You orbit one, distantly and safely, held in place by its gravity, even though you'll never see it directly, never hear its song with your ears, never feel its pull consciously. But it's there, always there, holding the galaxy together, keeping you in motion through space, maintaining the structure that makes everything else possible. You're made of atoms forged in stars, stars that themselves were born in environments shaped and influenced by black holes. The iron in your blood that carries oxygen to your cells was created in the core of a massive star that may have ended its life collapsing into a black hole. The calcium in your bones, giving them strength, was forged in stellar explosions influenced by the presence of these cosmic giants. The oxygen you breathe, filling your lungs right now as you settle towards sleep, was created in stars whose formation may have been triggered by energy from black holes compressing gas clouds. You are, quite literally, made of star stuff, as Carl Sagan so beautifully said. And black holes are part of that story, part of your story, part of the great cosmic narrative that includes everything from the Big Bang to this moment, to you lying here, breathing, thinking, feeling, existing. You're a way for the universe to know itself, to experience itself, to reflect on its own nature. And right now, in this moment, the universe is using your consciousness to contemplate black holes, those most extreme expressions of gravity and space-time. That's extraordinary when you think about it. The universe has been around for nearly 14 billion years, and for most of that time, it had no way to think about itself, no way to wonder, no way to ask questions or seek answers. And then, just recently on cosmic timescales, in just the last few billion years, life emerged on at least one planet. And then consciousness arose. And then that consciousness became curious about the cosmos that created it. And now, here you are, a temporary pattern of atoms arranged into a thinking, feeling being, contemplating the nature of black holes and your connection to them. And somewhere, right now, as you close your eyes, 26,000 light years away, a black hole is still singing its deep note. That B-flat 57 octaves below middle C. A hum that's been resonating through space for billions of years. It started singing long before Earth formed, before our solar system existed, before any of the atoms in your body had been brought together. It's singing right now, will sing tomorrow and the day after, and for billions of days to come after you're gone, after humanity is gone, after Earth itself is gone. It's a constant in a changing universe, a reminder that some things persist even as everything else transforms. Some patterns endure, some songs continue, and you can rest knowing that song continues, that the cosmos hums its lullaby, that even in the deepest darkness there is music, there is pattern, there is structure, there is something like peace and harmony underlying all the chaos and change. Remember, as you drift, that time is flexible, that it stretches and bends, that the moments you have are not measured the same way everywhere in the universe. Remember that black holes aren't empty, but full, not holes, but presences, the most concentrated form of existence, matter compressed to its ultimate essence. Remember that they glow, eventually giving back everything they've taken, that nothing is forever, not even the eternal night, not even the darkest places. Remember that they create as much as they destroy, that they shape galaxies and birth stars, that endings and beginnings are one, that destruction and creation are partners in the cosmic dance. Remember that you orbit one, that you're held in place by its distant gravity, that you're part of a system that's been turning for longer than you can imagine and will continue turning long after you're gone. And as you drift away now, as your breathing slows and your thoughts become soft and scattered like leaves falling in autumn, as you cross your own event horizon into the darkness of sleep, remember this above all. The universe is vast and strange and beautiful, full of mysteries we've only begun to explore, full of wonders we can barely comprehend. Black holes are among the deepest of those mysteries. Objects that challenge our understanding, that push our theories to their absolute limits, that reveal how much we still have to learn about the cosmos we inhabit. But they're also teachers, patient teachers, who've been waiting billions of years for us to notice them, to study them, to begin to understand their nature. They're showing us that reality is gentler than we fear, more flexible than we imagine, that even the most extreme places follow rules, beautiful mathematical rules that we can discover and understand. There is poetry in physics. There is beauty in the mathematics that describes black holes. There is wonder in the fact that we can understand them at all. You are part of this universe. You are connected to everything in it, including the black holes, those dark hearts that beat at the centers of galaxies with a rhythm measured in millions of years. And that connection means you're never truly alone, never lost, never adrift, never without a place in the grand structure of things. You're part of something so much larger than yourself, so much more ancient, so much more enduring. You're part of the galaxy, part of the cosmic web, part of the great unfolding of existence that began nearly 14 billion years ago and continues still, continues in you, continues in your breathing, your heartbeat, your consciousness settling into sleep. So sleep well, traveler. Sleep deeply and peacefully. Let the cosmic lullaby carry you away into dreams. Let the knowledge of black holes, of time dilation and event horizons, of Hawking radiation and spaghettification, of singing darkness and creative destruction, let all of it settle into your mind like sediment drifting slowly to the bottom of a still, deep pool. The universe is still unfolding, still expanding, still evolving, and you are part of it. You always have been, since before you were born, since before Earth formed, since the atoms that make you were forged in ancient stars. You always will be part of it, in one form or another, your atoms enduring even as their current arrangement changes, transforming eventually, joining the great cycle once more. Your atoms will endure, will transform, will perhaps one day be part of something else entirely, something new, something we can't imagine. Perhaps they'll be part of a star, fusing hydrogen in a core millions of degrees hot. Perhaps they'll be part of a planet, a world orbiting a distant sun. Maybe even a world where new life emerges and wonders about its place in the cosmos, just as you're wondering now. Perhaps they'll drift through space for eons, floating in the darkness between stars, patient and eternal, until gravity gathers them into something new. The atoms that are, you have already been many things before they were you. They've been through countless cycles already, and they'll go through countless more. You're a temporary arrangement, a brief pattern, but you're also part of something eternal, the endless transformation of matter and energy through the universe. But for now, for tonight, all you need to do is rest. All you need to do is breathe, slowly and deeply, feeling your chest rise and fall, feeling the air moving in and out, feeling yourself settling more and more deeply into comfort and peace. All you need to do is let go. Release your grip on wakefulness. Allow sleep to take you gently across its threshold. The black holes can wait. They've been waiting for billions of years already. They'll wait a few more hours while you sleep. The mysteries can wait too. They're not going anywhere. Tomorrow, if you wish, you can wake and wonder again, can think about these cosmic extremes, can read more, learn more, contemplate more. But tonight, let sleep take you gently across its event horizon, into that soft darkness where thoughts dissolve, where time moves strangely, where you're held and safe and at peace. And as you fall into dreams, into that soft darkness where thoughts dissolve and time moves strangely like it does near a black hole, perhaps you'll remember one last thing, the most important thing. Somewhere in the deep cosmos, right now, a black hole is still humming its ancient note, still singing that song that began billions of years before you were born. And you, traveler, you are made of stars. You are made of atoms that were forged in stellar furnaces, scattered through space, gathered by gravity, formed into planets, and eventually into you. You are star stuff contemplating star stuff, the universe knowing itself, experiencing itself, marveling at its own mysteries. You are part of the music, part of the great cosmic symphony. You are part of the light that dances around the darkness, part of the matter that swirls in accretion disks, part of the energy that flows through everything. You are part of the universe knowing itself, experiencing itself, marveling at its own mysteries and finding them beautiful. Sleep well. You've earned your rest. You've journeyed far tonight through concepts that challenge the mind, through ideas that stretch understanding, through cosmic extremes that exist at the very edge of what's possible. And in the morning, when light returns and you open your eyes again, you'll wake to a universe that still contains black holes, that still contains mysteries deeper than darkness, that still contains you. And that, perhaps, is the most beautiful mystery of all. That in a universe containing black holes, containing cosmic extremes, containing forces that can tear apart stars and bend time itself, there is also you. Conscious, aware, capable of wonder, capable of understanding, capable of finding beauty in the mathematics and poetry in the physics. You are the universe contemplating itself, and that's extraordinary. Rest now. Let go of everything. Let go of thoughts, of worries, of questions, of wonder even. Just drift. Just breathe. Just be. The universe will still be here when you wake, vast and strange and full of wonders. And so will the black holes, patient and eternal on human timescales, singing their songs, bending their time, holding their secrets, waiting for us to learn more about them. They'll wait for you. Everything will wait. The mysteries are patient. The cosmos is in no hurry. It's been unfolding for nearly 14 billion years. It can wait through your night of sleep. For now, just breathe slowly and let the rhythm of your breath carry you deeper into rest. Breathe in and feel yourself filling with the oxygen created in ancient stars. Breathe out and feel yourself releasing, letting go, surrendering to sleep. Breathe in and feel connected to everything, to the stars, to the black holes, to the galaxy, to the universe itself. Breathe out and feel yourself becoming softer, more diffuse, more like a dream than a person. Breathe in, slowly, deeply, peacefully. Breathe out and let the darkness embrace you gently. You are safe. You are held. You are part of something infinitely larger than yourself. And that is enough. That is everything. That is the gentle truth that carries you into sleep, that holds you through the night, that will be there when you wake. Good night, traveler. Rest well. May your dreams be full of stars and the beautiful darkness between them. May you drift through the night like matter drifting through space, peaceful and patient and at ease. May you wake refreshed, restored, ready to wonder again at this strange and beautiful universe we call home. Sleep now. The black holes are singing. The universe is humming its lullaby. And you are part of it all, always have been, always will be. Sleep and dream of cosmic wonders. Sleep and let yourself be held by the same forces that hold galaxies together. Sleep and know that you are exactly where you're meant to be, exactly what you're meant to be, exactly when you're meant to be it. You are the universe experiencing itself, and right now, the most natural thing for you to do is sleep. So sleep. Sleep deeply. Sleep peacefully. Sleep well. The cosmos wraps around you like a blanket. Time stretches gently into dreams. The black holes keep their vigil. And you, made of stardust, drift into the darkness, safe and held and home.